Hey everybody, welcome back to Spatial Stats. Last time we took a look under the hood of point pattern models. We discussed quadrature, how the different tiles are weighted, and we analyzed a simple toy data set using three techniques, one of which was the official StatStat application, the R package that we'll be using for point pattern analysis from here on out. Today, I want to run through a relatively simple example. We're going back to London. We're going back to London in 1855 when they were having a bit of a cholera outbreak. When we were learning about the exploratory data analysis, here was the kernel density plot that I made. And we have the pumps as the x's. The density of the cholera deaths is shown with different colors. And of course, we can pretty easily identify pump number one, the Broad Street pump, as the offending pump. So today I want to sort of run through how we analyze this data using official point pattern methods in the StatStat package. So one of the, I think, harder things to do with point pattern analysis is getting everything kind of ready to be analyzed, because once it's all set up, it becomes a log linear Poisson model. That's all point pattern analysis eventually boils down to, is a log linear Poisson model. But there are some careful ways in which we require that we enter the data, we make the observation window. So let's run through those really quickly here. The first thing we have to do is we have to decide on what is an appropriate observation window. So I haven't seen too many analyses of these data, but sometimes people take the outside edges, roughly speaking what I just drew on the screen, the outside edges of the observed data as the observation window. There are several reasons why that might be a bad idea. Remember that in theory, the event could have occurred anywhere in the observation window. Just because you use the outside edges of your point pattern to define the observation window doesn't mean that your event was impossible just outside of it, right over there, right over there. My recommendation would be to use a reasonable window defined by something other than your observed data, because I think there is a great potential to bias your analysis there. Why couldn't there be a cholera death right there, or even right there? I was really looking for the Soho neighborhood of London for a long time, but I settled on the West End ward. I think I showed this to you a few lectures ago. We're still looking at an area of about 2 square kilometers. So we're still looking at a pretty small area. The next thing we have to do is we have to set it as a OWIN, which is observation window object, and I rescale everything into kilometers. The other tricky bit is we really have to keep track of the units we're using. If our coordinates are in meters, then everything has to be in meters, including the area of our observation window. So if my coordinates were in meters, I couldn't use kilometers for my observation window. That is why, because I rescale my observation window into kilometers, I also manually, to demonstrate what happens, manually rescale the meters easting and meters northing into kilometers easting and kilometers northing. Finally, when I have my observation window and I have my basically matrix or data frame of the coordinates of all the points that we've observed, the actual point pattern, we define a point pattern object. We give it the X, the Y, and the observation window. So let's pick it up right there. Let's pick it up right there. Again, to emphasize, I project everything. I downloaded these shape files from a source that I gave you on the lecture notes, and I project everything using this British national grid, so everything comes out in meters. The deaths, the pumps, and the wards, which I then grabbed the West End ward from that file, everything comes out in meters, easting and meters northing. Whoops. And I run through, remake everything into kilometers, and let me run through that particular line. So it gives me a warning. It says that 3 points were rejected as lying outside of the specified window. So let's go back here. If you notice on this map, here is the boundary of the West End ward. And these 3 points are outside of the West End ward. So what R is telling me that there were 3 points lying outside of the window, and so I can't analyze them, right? I can only analyze what is inside my window. I'm okay with that, to be honest with you, because if I really think that it's pump 1 that is to blame, these are pretty far from the offending pump. So I'm okay with leaving them out of the analysis. What would be a way to include them? Well, include whatever this ward is called as another extension of the observation window. But then, it probably extends, somewhere out here. I'm probably biasing the average intensity at that point, because I am assuming that people who went to pump 1 could have lived anywhere in my observation window. And I think that is inherently also a false assumption. So I keep saying it, but it's super important. Be careful how you specify the observation window. Sometimes let a couple of points sort of be excluded, and that is okay. The other warning that R gives me is that data contain duplicated points. We assume that every point, the coordinate is known without error, and there are no duplicates. Now that you know what the inner workings of point pattern models are, how would you assign a unique weight, quadrature weight, to a duplicated point? Remember, we have to partition the entire window, right? We have to partition the entire window using quadrature weights with dummy points. How would you partition the window such that every single tile, all the tiles add up to the area of the window if you have a duplicated point? There's not a good way of doing that. So there is a simple way to only retain the unduplicated, the unique points. Let's just use the unique function as I do right here. Now I can run a quick summary command just to make sure that I didn't make a mistake. Sometimes the way that I've made mistakes is I wasn't careful enough when I was tracking the coordinate units, and I come to this step and it says that all of my points were rejected because they were lying outside of my observation window. How does that happen? You project your observation window using one projection, and you project your coordinates using a different projection. All the coordinates then lie outside of the observation window, and R says, no, we're going to reject all of them because they don't line up. What's another one? Sometimes you will find data sets where the longitude doesn't have a minus in front of it. If all the data come from the Western hemisphere, sometimes they exclude the minus sign in front of the longitude. If your observation window does have negative signs in front of the longitude, then again, R is going to perform sort of a formal check and tell you that all of your points have been rejected because all of your points are lying outside of the observation window. So although this is just a simple check, it is still worth it to make sure that you have roughly the number of points that you think you had. We had tried to put in 578 cholera deaths, and we're left with 572 after excluding a few duplicate points and 3 points that were just a touch outside of our West End ward. You can always make this plot right here as well, and it will show you that most of the data are concentrated in the eastern portion of the ward. That will come into play. That'll be an important low factoid as we start building models. But yeah, nothing exciting going on here. Really, the other thing to look at is that, again, the units are what you expect them to be, and to sort of make sure that this passes your BS detector, that R thinks you're doing what you are intending to be doing. All right, moving right along. We think that pump 1 is the offending pump. So remember, spatial covariates have to be defined everywhere in your observation window. A very natural covariate is the distance from pump 1 to everywhere in your observation window. And that is what this very beautiful graphic shows. Now, in order to make a covariate that is distance from pump 1 to every point in your observation window, again, that's every point in your observation window, whether or not you recorded a cholera death there. We had no cholera deaths out here, and accordingly, we're far away from pump 1. So for now, that covariate makes a ton of sense. Now, in order to make this happen, we have to, oh, that's a misspelling. We have to first make the pumps themselves, or pump 1 in this case, into a point pattern object. In this case, with only one point. All right, let me flip back into R, show you what happens. Now, this pumps shapefile has 6 points, right? These are 6-point features. Again, notice the coordinates are in meters, easting and northing. There are names of these pumps. Pump 1 is the offending Broad Street pump. I'm going to select that pump alone out of my set of 6 pumps. And now I have to make that one pump into its own little point pattern object. But first, keep the units consistent. I need to rescale my meters into kilometers. Now we have to keep that in mind. Rescale the meters into kilometers. Say that it was in the same observation window as my cholera deaths. Run this and make sure that I get what I think I'm getting, which is a point pattern with just one point. In this case, the observation pump. The offending Broad Street pump. Now, I get to use a handy dandy function called distmap, which does what you think it does. It produces a map of distances around our point pattern object. So if I run this, it computes the distances from our point, which represents the pump, to every point inside of our observation window. I can plot it, and it will produce this beautiful figure to which I added the pump, and I gave the West End ward boundary as well. All right, so now we have the point pattern, and we have a covariate. We can actually do a bit more of our exploratory analysis, and it's called this row hat function. I don't want to focus too long on this row hat function, just that it shows us how many more cholera deaths, how the intensity of cholera deaths varies with our covariate. In this case, the distance away from pump 1. It's essentially a ratio, and it's computing the intensity as a function of a covariate as a ratio to a uniform intensity. So if this were a flat line, then you would say there isn't that strong of a dependence. But again, this is there is no modeling happening here. This is still an exploratory analysis. Now, as you might imagine, when we're far away from the pump, our intensity goes back down to a uniform level. So dependence on distance goes down to 0. Then there is this linear bit in the middle distances. Then there's this interesting, what looks like a rise. So as we get a little farther away from the pump, within about 0.1 kilometers, right? And that's the other thing about units. All of our distances, all of our coordinates are in kilometers. So 0.1 kilometers, there are 1,000 meters in a kilometer. 0.1 kilometers is 100 meters. So within 100 meters, there is either no effect of distance, or there's actually some indication that as we get from really, really close to the pump to 100 meters away from the pump, the intensity increases relative to a uniform intensity. What this plot shows without fail is that there is a strong dependence of the intensity on the pump distance. And that dependence doesn't look particularly linear. Does not look particularly linear. We can just use this to spit back out a simple predicted intensity. Notice again, when we're really close to the pump, it's elevated relative to a uniform intensity. Then it increases, right? It increases to about, oh, I don't know, between 50 and 100 meters around the pump or thereabouts. Sorry, I flipped to the wrong image. And then it finally decays down to 0. I can just overlay my point pattern object to see how reasonable our distance is as a covariate. And it looks pretty darn reasonable. It doesn't mean, by the way, that outside of this circle, we can't observe a single cholera death. It just goes down to the baseline level that no longer changes as we get farther away from the pump. All right, we're now ready to fit some models. Poisson point pattern models, you can fit them in a few ways. There are several ways to control the spacing of those dummy points that you use to approximate the integral that is used to tell you what the expected number of points inside of your window is. Here is my quadrature scheme. You've seen this from last lecture. I'm using a 50 by 50 dummy grid. Why 50? I just picked a number. I can plot this quadrature scheme. It's already been pre-run. It runs for a few seconds, but you don't have to watch me watch R at that point. So here is my data, and then here are all the little dummies, and there are 50 by 50 with a corner dummy point, 50 by 50 with 4 corner points. Here it tells us the spacing, which is 0.04 kilometers, or about 40 meters by 40 meters is the spacing of the dummies. If our data was occurring on a much finer scale than that, you might want to increase the number of dummies. If our data, it looks like our data is occurring around on the same scale as these dummies. So I am roughly pleased with this particular quadrature scheme. There is another way to control dummy spacing, and it's via this EPS command. EPS that I'm setting here to be 0.01. This controls the dummy spacing in whatever the units that you specified are. So 0.01 says that I want my dummy spacing to be around 10 meters. I want a dummy point at every 10 meter interval. And I can run just this model by putting my point pattern object to the left of this tilde and my covariates, or no covariates at all, to the right of the tilde. And this looked like a mistake. So now if I output my model, which, by the way, this is a homogeneous intensity Poisson. We expect this to be blatantly ridiculous because this is a clearly clustered pattern. This model says that we have no covariates and we have just uniform homogeneous intensity across our observation window. So we expect these first couple of models to be blatantly ridiculous. Let me clear my window. And what I was trying to show you guys is that we requested 0.01 kilometer dummy spacing, but when we filled the space in our observation window, because it's an irregular polygon, we got actually slightly better than that. We got 0.099 by 0.099 actual spacing. We actually got slightly better than that. We have an estimate of the fitted intensity. That's 286 points per square kilometer. That corresponds very nicely to, if I just run intensity of my point pattern object, this tool will produce exactly the same result. And this is because we're doing exactly the same thing. If I run the same model, just fit to my quadrature scheme. Now remember, my quadrature scheme is, the dummies are spaced at about 0.04 kilometers. Here it's 0.01 kilometers. I'm gonna have essentially the same results, maybe different by a few decimal points, but that's not even the case here because I have no covariates. So by running the model to a more coarse quadrature scheme, I come up with exactly the same intensity as before. All right. That is not a particularly interesting set of models, but if you wanted a baseline to compare your models against, here's the AIC of both of my models. Whoa. I can come up with, I wonder if the AICs are even identical. So those are, pretty much identical models, even though the dummy spacing was ever so slightly off. We know that the intensity of cholera deaths varies with pump distance. So remember that we specify our models on the log scale. So what we're actually saying is that, I'm going to insert a flat, empty slide. What we're actually specifying is that the log of my intensity, all right, varies as a function of distance to the pump. Now, what we observe, this is the log of the expected number of points per square kilometer. What we observe is the points per square kilometer. So I'm going to take this to the power of E. And so my intensity, expected number of points per square kilometer, notice that our regression model goes into the exponent. And so, that here is maybe the baseline. And then this is the part that varies with distance. So let's just develop our intuition about what happens. As distance goes to 0, as we get really close to the pump, all right, as distance goes to 0, I have e to the power of 0, which goes to 1, then the intensity goes to my baseline, which is e to my intercept. As we get really, really far from the pump, as distance from the pump goes to infinity, what happens to my intensity very much depends on this coefficient. If the coefficient is negative, then the intensity goes to 0. Because we're taking some value and we're dividing it by e to the infinity, right? Taking something to a negative power is the same thing as performing this division. Okay? So it very much depends on, as we get really far away from the pump, it very much depends on the coefficient of distance as to what happens to the intensity. Let's take a look. I may have said a few lectures ago that these models look super simple to specify. I could have run it without this EPS statement at all. I could have, this is just going to run, and I will get parameter estimates. The reason why I even made the all of last lecture is so we can understand what this model is even doing, because this is so deceptively simple. In fact, this is just going to give us whatever the default spacing of our dummy points was. So it looks like the default spacing was a 64 by 64 grid. Remember, I requested a 50 by 50 grid. The default was a 64 by 64 grid, where this was the spacing, about 30 by 30 meters. If I put this back, this is going to give me my 10 by 10 meter spacing, even slightly better than 10 by 10 meter spacing. So this is a more fine grid than what was in there by default. Flip down and take a look at the coefficient. Okay, look, it's a negative number. So now this corresponds nicely to this case. As we get far away from the pump, our average expected number of points per square kilometer goes to 0. We don't expect people to be dying from cholera as we get really far away from the pump. I could also very easily fit the same model to my quadrature scheme, and it'll produce virtually identical results. If I just run this coef command, you will notice that they're not completely identical. In fact, the dummy spacing does make some difference, but it is not a discernible difference. And back to the notes, I'm sorry, I'm flipping around a bit. You can't tell if I plot the model-based estimate of how the intensity varies with pump distance. You can't tell which one was fit to a 10 by 10 meter dummy set or a 40 by 40 spacing of the dummies. All right. But we know that model building is more complex than that. I have shown that, not surprisingly, our intensity varies pretty strongly with distance to pump. But the question is that linear on the log scale? Is that nonlinear on the log scale? If you remember our rho function, our non-parametric look at how intensity varies, we see that this is not linear. It's flat to increasing at small distances. So it might make sense for us to play around a little bit with that distance function, with the function of how distance affects expected intensity. And so that's what I do here. First of all, we can run this diagnose command, and it will give us the spatial residuals. So we have a nice little set of plots. I'm going to direct you to the top right, bottom left, and bottom right set of plots first. So this is the cumulative sum of the Pearson residuals as we move east to west or west to east. This is the cumulative sum of the Pearson residuals as we move south to north. Notice that we're doing great until we hit the area near the pump. And then we get this large sort of negative excursion. The residual is observed minus expected. So we are over predicting the number of cholera deaths, roughly at this point. And there is less systematic deviation along the north-south axis, but consistent with the cumulative residual plot, we also see that there's clearly a pattern in the spatial residuals. We are over predicting the number of cholera deaths right there where my cursor is, because that's a negative residual. Our residual is observed minus expected. So what a negative residual means expected was greater than observed. We're over predicting the number of cholera deaths there. We're under predicting the number of cholera deaths there. Now this looks like a fairly simple pattern for us to correct. And I'll show you how to do it in a sec. The R package allows you to output a pseudo R squared of 51%. I don't have a good feel for what values you should be expecting, but not surprisingly, Just one covariate and an intercept explain about 50% of the variability in intensity. That's a pretty satisfactory result. We also have this QQ plot, which you might remember from your regression class. And I run everything with a Pearson residual because Pearson residuals have a mean of 0 and a standard deviation of 1. So we always get to know how large of a residual is large and how small of a residual is small. A Pearson residual of 3 or minus 3 is huge. A Pearson residual of 1.2, generally not that large. So in a QQ plot, as per usual in our regression model, we have our data quantiles and sort of expected simulated quantiles, and really wanted to follow that diagonal line. And it produces these uncertainty bands. So it's okay if our QQ plot falls inside the uncertainty bands. This clearly doesn't. So our residual diagnostic shows that we're missing something. We're missing this west to east gradient. And our QQ plot doesn't look too good. We're not really following the diagonal line there. So we're missing something. It could be that we're missing a nonlinear effect of distance. So here I simply say, okay, well, what if, I'm going to flip to the notes. What if intensity varies as a function of square distance? And again, what this means is I actually have a square. We expect that coefficient to be negative, really do. We actually have a squared term inside of an exponent. Maybe that will give us some kind of a peak or at least a flat area when the distance is close to 0. That's what I'm hoping this is going to do for me. Again, I'm keeping, at this point, you will notice I'm just fitting the models straight to the point pattern object. I could be fitting them to the quadrature scheme. I just feel it's a little bit more convenient to specify your dummy point spacing this way. Again, this is a 10 by 10 grid. Fit my model, it runs fairly quickly. I look at my estimates. Not surprisingly, that's a negative coefficient. Again, everything is highly statistically significant. I'm trying to visualize what this looks like. The difference is I do have a little bit of a flat area when we're really, really close to the pump. That intensity doesn't drop precipitously. It changes more slowly when we're near the pump and then quickly as we get a little bit away from the pump. So I'm thinking this is a better model. Let's take a look at my residuals. All right. This looks potentially better. I look at my cumulative Pearson residuals as I move east to west, west to east. I am now not exceeding these 2 standard deviation limits, but there's still something happening, right? I'm not, the north-south looks really good at this point, now that I've included the squared distance term, but I'm not entirely pleased. Over here, I'm still getting this over prediction right over here, under prediction right over here. Right? These are positive residuals, observed minus expected. I'm observing cholera deaths, and I'm not predicting cholera deaths there. Okay, so I'm still missing something there. My QQ plot, by the way, it generates however many simulations you have here. It looks a little better. We're starting to straighten it out, but I'm still outside of my uncertainty bands. So I'm, gathering evidence that there's still something missing. I'm not going to go through this right now in the interest of not boring you, but I also tried, for the sake of trying stuff, a piecewise distance effect. So it's going to be one type of effect when we're within 0.15 kilometers of the pump, and a different one when we're outside of 0.15 kilometers of the pump. Let me cut to the chase. Based on this image, we're missing a west to east trend. I do have the ability to use the XY coordinates themselves as covariates. And here in my model 2, if I'm going to use one coordinate, I may as well use the other coordinate. And I may as well estimate an interaction between them. So I simply center and scale my easting in meters, and I center and scale my northing in meters. Again, here is my dummy spacing of 0.01 kilometers. Run this model, still have the squared pump distance. I'm far more happy with how that decays when I'm really close to the pump. Run the summary command, and it actually tells me that everything was significant. My interaction term was actually significant. My squared pump distance was significant. So I feel happy about that. Let me look at the residuals. All right, now we're really starting to look good. First of all, here is the standard deviation of that, the Pearson residuals, 1.2. Notice that we don't even come close to exceeding anything that resembles like 2 standard deviations. And we don't have a systematic pattern as we move east to west. We don't have a systematic pattern as we move south to north. And although this does produce an area of positive residuals there and an area of negative residuals there, if you look at the magnitude, it's like 1 there and -1 right there. That is within or around 1 standard deviation. So that does not constitute a significant lack of fit. So I am particularly pleased with my model 2. Let me look at my QQ plot. I really want that to resemble that nice diagonal line. Looks like I decided randomly to run it for 20 simulations. So we'll have to look at each other for just a couple of minutes. And there it is. You know what, guys? It's not perfect. It's not perfect, right? We have it follows our line right there, and it gets out of it right there. Far better than Model 1, any of the Model 1 specifications. I can look at my R squared term, and that ticks up by a few %. But we know that we can't use R squared for model selection. So here, I'm just going to run through an AIC comparison. M0, if you remember, was my homogeneous Poisson model. We know that's ridiculous, and we do get to produce kind of a baseline AIC number. Here is the AIC of the linear model, the model where the relationship between distance and intensity is linear. Here is where it's quadratic. Here is piecewise. Looks like I didn't do better when it was piecewise. And finally, M2 is when we include the coordinates themselves as covariates. Well, look at that. That's the best model as far as AIC goes as well. That's also the best model as far as the QQ plot goes, and the best model as far as our residual diagnostics go. So I select model 2. I choose you, Pikachu. So it's time to make some predictions. Here is my predicted intensity using my model 2. And I just wanted to compare to my initial plot, my exploratory plot. This is my model-based prediction. A few things to look at. By including those coordinates, you can see that it moved this area of high intensity away from the center of the pump, right? It moved it southeast somewhat. And this corresponds to most of the cholera deaths occurring south and southeast of the pump and not north and northwest of the pump, right? Our area, our blob got moved southeast. That's what including those coordinates did. Correctly, we're not picking out any of the other 5 pumps, but we're allowing for the possibility that you might just live right there, and we expect that some cholera deaths will be occurring. So I am, again, very, very pleased with how my model fits. Okay, so this pretty much wraps up today's lecture. This was basically a start to point pattern models. Next time, I want to go through a far more involved example with some larger scale data. And specifically, one thing to think about as you guys are going into the weekend, small areas are relatively easy to model. There's only so much evil you can do with your statistical model when you look at a really small area. Remember, we're looking at 2 square kilometers here. You know, the influences in a 2 square kilometer area are more well defined than if I start looking across continents. And next time, I'm going to give it a shot to fit some cool point pattern models to continental level data, at least far larger scale than 2 square kilometers. So tune in next time. You guys stay safe, do your homework, and thank you guys. Take care.